Professor Johannes Margraf. He studied chemistry at the University of Ellingen, where he also obtained a PhD. He joined the quantum theory project at the University of Florida as a postdoc funded by Theodore Linden Fellowship. This was followed by another postdoc fellowship at the Technical University of Munich. In 2021, he became a group leader at the theory department of Fritz Auer Institute in Berlin. Since 2023, he holds the chair of physical chemistry, fire theory, and machine learning at the University of Aveiro. His focus on using and developing machine learning and electronic structured methods to study chemical reactions and discover new functional materials. Thank you.
Thank you very much. Yes, thanks again, especially to the organizers for inviting me and for putting this beautiful workshop together. It's been very inspiring to see the other talks and also to talk to some of you. So the title here is very generic, and I think there's going to be a lot of overlap with the previous two talks, but nonetheless I think, hopefully I can provide a little bit of a complementary perspective here. So, as just mentioned here, does this work? So, I think in the program I'm still mentioned as in the Fritz Haber Institute here in Berlin. So in September I moved a little bit south to the University of Bayreuth. This is our very nice campus. Bayreuth, if you know it, you might know it because it has a very famous Wagner festival. So this is where Wagner spent a lot of his time. But it also has a nice university, and it now has my group there. So this is my group in Bayreuth, and this is kind of a little bit older picture from the Berlin people. So half basically stayed behind in Berlin, the other half moved to Bayreuth, and we're still, very actively collaborating, of course, with the people in Berlin as well. So before I get to kind of the talk itself, I thought as part of the introduction I could also show a little bit about broadly what we do. So I usually split this up into these three overlapping fields. So we work a lot on interatomic potentials, which of course we've just heard about what those are. We are very interested in enhancing machine learning methods by introducing physical concepts and physical models into them. And then a lot of our applications are geared at designing molecules and materials. I think this is, of course, also of interest here. So in the interatomic potential field, what I'm really interested in is that we can take the accuracy of density functional theory of DFT calculations, atomistic DFT calculations, that allow us to accurately predict structures, to study chemical reactions, and we can speed these things up by a few orders of magnitude. And that really changes what kind of science we can do with this. So we can look at very complex chemical reaction networks. We can do very thorough global optimization studies of structures. And this has motivated me greatly because I come from kind of the different structure field, and I've always been frustrated by the fact that we have to do a lot of compromises in how we describe the atomistic structure of things. We always look at kind of simplified models, and I think the interatomic potentials, the machine learning potentials, are really allowing us to make much more realistic and atomistic models of materials. I think this is a really important bit here. In terms of the physics-enhanced machine learning, I think a very nice thing is that if you're interested in electronic properties, like, for example, Alessandro showed in orbital energies, excitation energies, these kinds of things, you can take advantage of certain physical properties of these things. For example, they might be localized, they might have a certain size scaling, for example, be size-intensive, and you can build this into the machine learning models and have them be more robust and extrapolative in that way. And of course, also, as has been mentioned, the electrostatics are a really important issue, and I'm going to explain a little bit why and how we can address this later on in the talk. And then finally, of course, the designing the materials and molecules. I think everyone here understands and knows why that is important. So we've done also some work in organic materials here, together with the group of Harald Oberhofer and Carsten Reuter, and a lot of interest, especially in my time in Berlin, has been on inorganic materials, on solids and surfaces and catalysts particularly. All right, so that's kind of just the very broad overview. Now, of course, you all know what machine learning is, but let me still give you my perspective on it, right? So basically what it is that we are learning some complicated function from data, and this can be illustrated as in this movie. So we have 2 data points, we fit a function to it, and by collecting more data, we can kind of update our notion of what the underlying function looks like. And what you can see is that the new points that are coming in are being, of course, accommodated by our function. And as we collect more and more data, the red points end up lying on this blue curve. And that's how we learn the underlying function, basically. And the right side of this plot is showing the prediction error. So it's showing the deviation from the red points in the blue curve at each of these iterations. And you can see this nicely going down with training size. And this is what is very useful about machine learning compared to, let's say, conventional data fitting, right? So of course I can also fit a polynomial to this data here, but then I need to make a choice about what degree polynomial I'm using, and I would need to adapt the degree of the polynomial to more and more data. And what is cool about machine learning methods is that they have an intrinsic flexibility, and that usually we are regularizing them, either implicitly or explicitly during training, which means that the complexity of the function adapts to the amount of data I have. And that's why I can get, for a single learner, I can get this kind of behavior, and it improves its predictability on unknown data by being shown more data, right? And that means that I can kind of scale the accuracy of my model arbitrarily within limits. And these kinds of curves, where you see some error metric like an RMSD or a mean absolute error, and the number of training points, these are commonly called learning curves, and I'm a big fan of learning curves, so I'm going to show you a bunch of them. And this kind of behavior that you just saw, and I should say that this here is in a log scale, so both axes here are in a log scale, and then you have this kind of linear decay. This is very universal behavior of machine learning models. Right? So basically, this tells you that the error has some power law dependency on the number of data that you use to train. And yeah, I should give credit here to Anatol von Lilienfeld, who has been very like a missionary of this kind of representation in chemistry. And I think it's very useful because very often, of course, we have a certain amount of data and we fit the model for the data we have, so we're always kind of on the right-hand side of this plot, whatever the maximum amount is. But you can learn a lot about a model from also looking at what happens if I decrease the amount of data. And so there's kind of 2 regimes here that we end up being interested in, and I think a lot of you guys are working with experimental data where data is expensive and you cannot maybe do 100,000 or 1 million calculations easily, right? So you're kind of interested in the small data regime. So it's important to also check how well models perform in this edge. And so the things that are important here is that we need to be efficient about how we select data points, and we've already heard about Bayesian optimization and related methods that use uncertainty to select data, to maximize the diversity of your data set. This makes a really big difference. If you just have 10 or 100 data points, you can really gain a lot by efficiently selecting the data. And if you do this, and if you're doing this kind of iteratively, fast training times are also very important. Active learning is very important, and we also heard that concept before. And in general, you want to be robust, right? And your model's not going to be perfect, but at least it shouldn't do crazy things. It should fail in a kind of controlled way, let's say. And the methods that we use here, that's mostly Gaussian process regression. These are called kernel methods. And we've also heard about support vector machines and kernel-rich regression. So that family of methods, I think, has a really important role to play on this side of the spectrum. And then on the big data regime, and this is where Xipeng has shown a lot of interesting things. If you have, let's say, 100,000, a million data points, you can also use very sophisticated methods, right? And actually you need to worry about using algorithms that allow you to move to this scale, right? So the kernel method can be very efficient down here, but it will be insanely expensive to train for 100,000 points. So that's something to be aware of as well, right? So you need a scalable algorithm. These element embeddings for going to many elements are really a key thing here. And I think what is also very important is if you're going to do big data and you're going to spend a lot of effort on training your model and on collecting the data, your model better be transferable and useful in many applications, right? Because if you spend a lot of energy and time on training the model, and then your application is just one small example, that's just not economical. So transferability here is a big topic. And the tool of the trade here is graph neural networks, and especially what I call, so what is generally called equivariant or and directional. So I would call M3GNet a directional neural network. I maybe disagree, but we can talk about this. And the equivariant family, like maze models that we've also heard about. Okay, so how, let me be a little bit more specific now about what we do. So we do atomistic models. We do basically structure property relations. And that means that we need to represent the structure in some way. And there's my laundry list of things that this representation of the structure should do. So first of all, I want really to represent the full geometrical information, because in many cases I'm doing interatomic potentials, or I'm in general interested in how, for example, the dipole moment also responds to small changes in the geometry, because maybe I want to do a IR spectrum or something like this. Right? So I want the full geometric information, not these kind of chemoinformatic fingerprints. I want to be computationally efficient, because the whole point of the exercise is to be much faster than DFT. And there's other things, so the representation should be unique. I don't want two different molecules to map to the same representation, because that gives that sort of uncertainty into my prediction. And I want to build in known symmetries and invariances, like translational symmetry, rotational symmetry, and permutational symmetry that the total energy of a molecule has. That should be built into the representation. It should be at the core of the model, and it should not be something that the model needs to learn from data. And finally, what I think is extremely important as well, and shouldn't be overlooked, is the model should be size extensive, because I'm doing DFT calculations to generate my training data, and those scale poorly with size. So I can afford to do many DFT calculations on small systems, but I cannot afford to do very large systems, right? I can run a DFT calculation on 10 or 100 atoms, but I don't want to do it on 10,000 atoms. Right? So the whole point is that I want to be able to train on small things, predict on large things, and that's why size extensivity is very important. And the solution that the community has come up with in this context are basically these, as we've also seen in the previous talk, atomic environment-based representations. So there's the atom-centered symmetry functions of Bela, there's SOLT from Bartok and Kawachani, there's Anatol's FCHL, and then most recently the atomic cluster expansion of Ralph Downs. And what all of these have in common is that essentially they look at individual atoms, basically build a cutoff sphere around each atom, and then they represent the atomic environment within that sphere. Yeah? So instead of having one vector that represents your molecule or your material, you have for each atom a little vector that represents the atomic environment. And that's also how the size extensivity gets in, right? So first of all, this is cool because it makes things cheaper, right? I only ever need to look at these small chunks of atoms, right? So everything scales linearly with the system size. But then I can also build my model in such a way that, for example, the total energy gets predicted as a sum of these local energies, right? So the total energy here is a sum of E1, or epsilon 1, epsilon 2, epsilon 3, and so on. And this way, if I train on this small thing, and now I build a polymer out of it, my prediction will scale to the size, because I'm just predicting more small epsilon, and all of these are consistent. So I think this is a really important and useful idea. Yeah. Now, it should be noted that this is not a rigorous physical decomposition of the energy, but it's just an approximation we do to make the model have useful behavior for us and to make it simpler and more efficient to train. But it's also important to know that these atomic energies, I don't need to provide them during the training. So this is something that the model itself infers. I'm only ever training on total energies and forces, but nonetheless, the model, by its construction, works via these intermediate quantities. Okay, so that was background and a little bit of introduction. So now let me tell you basically 3 scientific stories, and maybe also introduce 3 important concepts that are, I think, very common now in the state of the art of materials modeling. So the first is about active learning. We've heard about this before, but let me just explain in a little bit more detail what is meant by that. So active learning essentially means that you are training your molecule in an iterative fashion, and you are actually using the model itself to generate new training data, right? I mean, that's actually not a requirement, but that's what is done in interatomic potentials. So say you do a molecular dynamics simulation, and you have some interatomic potential that can propagate your nuclei in time, or you're doing a geometry optimization, and you're doing optimization steps. So this means that based on energies and forces for some configuration, you can predict the new one. And now the cool thing is that in actually all machine learning models, you can also create uncertainty estimates that tell you how reliable that estimate is of the energies and forces. And based on this estimate, you can either say, I don't trust this prediction, I'm going to do a DFT calculation here, or you can go the other way and trust the prediction, update the configuration, and go on. Right? And the good thing is in a molecular dynamics simulation and geometry optimization, you tend to have many steps, right? You have 10, 100, maybe a million steps to run. And you're only gonna do the left branch of this, which is the expensive part, a couple of times, maybe 1%, 0.1% of the times. And the other times you can just trust the estimate, it gets better over time. So that's very, very useful. In practice, actually, this is not usually what we do. What we do is the thing here on the right-hand side. This is called offline active learning. So instead of doing this kind of configuration by configuration, what we like to do is we like to define some task, maybe a global optimization, maybe a geometry optimization to estimate some observable. And then we run the whole thing. We sample from all of the configuration that get generated, and we retrain and do this iteratively. This has the advantage that we don't need to constantly stop our calculation and have this complicated logic of branching, and we can do things in a kind of batched way, so it's computationally more efficient. And it also allows us to monitor how the observable we're looking at is actually changing over time, which is quite useful. So let me give you an example of this. In catalysis, if we're looking at something like synthesis gas chemistry, so CO and H2 and maybe water and CO2 are being converted to higher chemicals like ethanol or long-chain hydrocarbons on a transition metal surface like rhodium. Then you have a lot of intermediates that are potentially relevant here, right? So you go from CO and then you can hydrogenate it, you can build CC coupling steps, you can have decompositions. So there's a huge library of potential intermediates here. And we would like to know which of them are relevant to the reaction network and which ones are not, because at the end of the day, maybe we want to build a kinetic model of this process. And then it's a huge challenge to actually filter out relevant or unrelevant intermediates. And that's because if I have a little bit of a flexible molecule and I have a surface like rhodium-211 that is not completely flat and symmetric, then there's a lot of different local minima that this intermediate can have on the surface. So basically, to do this, I need to quickly sample different surface models, different adsorbents, and different configurations for these adsorbents. And here, active learning can be really useful. So basically, what we do is we run a minimal hopping simulation. So this is a global optimization of the adsorbent here on the surface. And we do this by training the model on the fly. And here, each iteration means one minimal hopping iteration plus one training of the model. And you can see that at first it is a very, very poor predictive accuracy. So the root mean square deviation on the forces is 4 eV per angstrom. This is insane. Yeah? But it doesn't really matter because the data that is generated is nonetheless useful for our model. In fact, you can see this here. So the initial model, because it has seen basically no data, it's very bad. So it's predicting that this molecule here will kind of sink into the surface and all of the angles are completely unchemical. But very quickly, we get rid of this unphysical behavior, and we have a conversion model that is very close to the final DFT prediction. And because this model is so much cheaper than DFT, we can do this search on a very large scale. And I think this is also an important aspect, right? Very often, even this is a fairly small system, so we can afford the DFT here. But for a global optimization, we want to also be confident that we've actually tried sufficiently large number of configurations. And with a machine learning model, you can do this. So you can do here 40 parallel simulations. You can see what is the lowest formation energy found across these 40 different runs. And you can see that, and it's a bit hard to see here, but basically the gray lines are all of the different parallel runners. And this global minimum here is rediscovered several times with several independent simulations, which gives us some confidence that this is really the global minimum. And this has some really tangible consequences. First of all, it gets us very quickly towards estimating, now within weeks, what is the binding energy for these different intermediates in a robust and confident manner. And we can actually revise some literature reported values like these by up to quarter eV, which is really a big energy for a catalytic setting. Okay, so that's kind of concept one, active learning, very useful if you have basically no data to start with, because you're fitting your model and generating the data in one go, and you're in some way being optimal about what kind of data you're collecting. So the second thing is going to be about electrostatics, and more broadly, I want to talk about inductive biases. So in machine learning, when we talk about inductive biases, we talk about the fact that even for a given training set that is fixed, I can build different models, right? So I can choose different hyperparameters for my model. I can use a neural network or a kernel method or a random forest model or whatever. So there's basically a space of different models I can do, and for the same training data, I can now train maybe 4 different models, right? And now I can apply these 4 different models to unseen data, and they will give me different predictions. And that's because each, so this process of predicting unseen data is called induction. And each of these models has different biases in how it does this induction. And you can see that if you have little data, all 4 of these models will agree on the data you have, but they will disagree between the data, right? So that's why it's important to have different inductive biases. And you can see that maybe this blue line here is a lot more conservative. It's kind of staying rather constant, whereas this green line here is more behaving like a polynomial, so it's widely oscillating between the data points, right? And so what your inductive bias is matters a lot in this situation. If you have big data, broadly speaking, so you have a high density of data, these differences kind of disappear because you're still forcing all of them to agree on the training data, right? So this is why thinking about the model itself and the architecture of the model and the structure of the model is very important in the small data regime, right? In the big data regime, it's a little bit different because then you have advantages of leaving a lot of freedom to your model as well, right? So there is some trade-off going on. But in the small data regime, I would always think about the inductive biases of my model. And one thing that is very important here, and this has been kind of work done by Jörg Behler and also previously by Stefan Gödecke, is to think about electrostatic interactions. So these are, as you know, long range, right? If I have an ionic material, so this is zinc oxide, I have partial charges, and essentially the Coulomb interaction decays as 1 over r here. But I previously told you that my machine learning model is only looking at the local environment, right? So it's kind of neglecting these things. And that can be problematic in sort of subtle ways if you compare these 2 slabs. So this is the same zinc oxide surface slab, but in one case it's deprotonated, in the other case it's protonated. And what you can see here, although it's not very easy to see, these are Hirschfeld charges for this surface model. And it turns out that actually the zinc atoms here are less positive than the zinc atoms over here. And this is only because I'm changing something on the other side of the slab, right? The slab has a dipole moment, it gets compensated, so you have no local charge transfer here. So we need to think about how we can describe these kinds of non-local effects in ionic systems, and we also need to think about external fields, right? So if you're interested in batteries, for example, but also in solar cells, or any kind of electrical device, electrochemistry, you can have external fields applied on your system, and if you want to study the response of your model to those fields, you better have some concept of electrostatics. So this is why this concept of 4th generation neural network potentials has been very popular over the last years. Again, it's coming from Behler here. And since we like to work with kernel machine learning in this small data regime, we kind of figured it would be nice to bring this concept of non-local electrostatics to the kernel models as well. And this is what we call KQEQ. So how does that work? Same concept as before. We have local environments, but now instead of predicting local energies, we are predicting local electronegativities, okay? So each atom now again gets a local electronegativity, but we're not just summing up over these. Instead, we are feeding them into a charge equilibration model. These charge equilibration models are actually well known, right? This is something coming out of classical molecular dynamics, where it's commonly used. But the key difference to what Lapierre and Goddard did originally, where every element, so every oxygen atom has the same electronegativity, we now use this responsiveness to the local environment to have a different electronegativity for each atom, and an electronegativity that responds also to changes in the geometry. And then you get, from charge equilibration, you get partial charges, so you can describe the non-local charge transfer in this way. And then you can build a total energy function that has a local contribution and a non-local contribution from the QEQ, basically. And just to illustrate why that's kind of a cool thing, so the first application we did here was the prediction of molecular dipole moments for small organic molecules. And here you see the relative dipole error for the QEQ model. And you see that the QEQ model is not a machine learning model because it's not improving as I shown more of training samples, right? It's just the fact that every element has the same electronegativity is too restricting and it cannot adapt to more data. Whereas the KQQ model, which has this machine learning aspect, it learns from more samples. And also, even for the smallest training set, it's already better than the classical model, right? So this is also a big advantage of using this inductive bias here. It's a very data efficient model, basically. And then you can compare it to a classical machine learning model that might just predict the dipole moment for a given, based on the structure. What is nice here is you can also look under the hood, how does this prediction of the dipole moment come to pass, right? Because it's based on predicted partial charges, and you can kind of see that this is physically reasonable what comes out, and we can even compare it to quantum chemical charge distribution in this case. And again, illustrating kind of this concept of inductive biases, here you have a comparison of different machine learning models. So I apologize a little bit now, the scale has changed, so this is now the log scale. Mean absolute error of the dipole moment against the number of training points. Here's again the QEQ model, here's our KQEQ model. And you can see the FCHL, so that would be kind of a naive model. That's just using a structural descriptor to predict the dipole moment. I mean, it's also learning, but it has a much larger error. It even has larger error than the QEQ model, the classical model. FCHL star has a better inductive bias because it models the dipole moment as a response to a field, essentially, right? And so even though you're using the same representation and the same data, FCHL star is a lot better. And then down here you have MUML by Michele Cervetti's group, which uses a different inductive bias than we do. So in this case, they are modeling the charge distribution in terms of local atomic dipoles as well as local atomic charges, right? So they have a more sophisticated model of the charge distribution. And you can see that in this case, these two different inductive biases we choose, either using this charge equilibration route or the local dipole route, have a very similar performance. And you can really see that even if you have the same kind of training data and the same kind of descriptor, in this case, MUML and KQEQ both use a soft descriptor, it can make a difference how you're building the model. Now, currently we are kind of developing this further, so also Martin Wondag in my group has built now interatomic potentials based on this, which are quite nice. You can do predictions on ionic materials, you can look at charge distributions for nanoparticles here, zinc oxide nanoparticles, also solids. You can see here we can study charge defects, for example, defect pairs and this kind of stuff. And we can also look at how these properties depend on the local charge state of the model, which has also not been possible previously. All right. Now let me get to the last part, and this will be directly connecting to what we heard now about M3G net previously. So what happens if I go now from the left-hand side of my learning curve, from the small data regime to the big data regime? How can I build, big data-based models? And we already heard about the materials project, so this is certainly one of the very unique and incredibly useful sources of data. There are also others, and I'm going to show you an example for QM7X. So this is a molecular data set that contains many diverse organic molecules and non-equilibrium geometries. Another example that I think is very relevant in the catalysis example is from Zach Ulissi and people from Facebook. Is this open catalyst project where they looked at a lot of different surface atomate pairs, right? And each of these basically has millions of configurations. So the OC20 has, I think, 250 million single quantity T calculations. QM7 has about 4.2 million. And the Curious project, if you include all of the realization trajectories, has about 1.5 million configurations for 150,000 inorganic crystals. And the fact that we now have these databases since the last couple of years has really opened up new opportunities. So we need to use a little bit different design principles for our models. I think this has already been introduced, so let me just run through it. Again, we use this local representation as a basis because it has a lot of nice properties, right? It's size extensive, it's computationally efficient, and so on. It has these rotational invariances and so on that we want to have. But then we expand this, first of all, through this message passing mechanism. So this means that not only do we consider here the local environment, but we also allow this local environment to communicate with the other local environments, right? So this expands my receptive field. So now the model is a bit longer range because of that, but more importantly, it also has some higher body order information because of this. The element embeddings have been nicely shown already, so these are essential for making these kinds of models. Otherwise, you could not make a model that scales to so many elements. Order 80 to 100 elements as now possible. It's not been possible before. And I think what a very important component is to have some kind of directional information that goes beyond just the pairwise interactions, basically, pairwise distances between atoms. So in the case of a GNet or DiNet or GenNet, that would be angles and dihedrals, right? That's directional information, or you could say 3- and 4-body information. And in the case of NECWeb and NACE, which are models that we've been using now, this would be essentially the equivariant information. But either way, having this is very important. So the initial models here, like Schnepp and Hebenen, that introduced this message passing concept to atomistic modeling, did not have this kind of higher order information and were thus not as accurate. So what can you do with this? So first let me give you a molecular example. So this is the QM7X database. I mentioned this, 2.5 million configurations, I think, no, actually 4.5, I think. Basically different organic molecules, different non-equilibrium structures. And now you can see, again, these learning curves. So this is the training set size. This is the mean absolute error on the forces. And you can see it goes down, at least up to around 320,000 training samples. Then it more or less saturates here. That's a sign that essentially we are now reaching the intrinsic accuracy of that data set, right? And you can see a big difference here. So Schnepp is this original message passing network with 2-body information. DiNet has 3-body information like M3GNet. GenNet also has 4-body information. And you can see that really also helps, and actually helps no matter what the training set size is. So even for 3,000 configurations, having this additional information improves the models. But what's interesting now, so this is a test set error. So this is basically, we split the data, we train on one part, and we predict on the remaining part to see how well it predicts, right? And this looks very good. So here I'm just showing you the best curve, basically the GenNet curve over here, in a different plot. So 10 to, this between 10 to the minus 2 and 10 to the minus 1 EV per angstrom error is about as good as I want to get from a normal geometry optimization. So I could be happy with this model if I could trust this. But the point is, you can't really trust it like this, right? Because if I now take these 20 molecules here, and they are all in the training set, and I run molecular dynamics, it turns out that the predictive error on the molecular dynamic structures is much, much larger than my tested error. And this is what is called, I think you mentioned this also, the robustness of the model. It's not there, it's just not robust. It looks very well when I do the training, but it doesn't really generalize. And if I now increase then the temperature, you can also see that this model here has very, very large errors. So this is on the order of 10 EV per angstrom errors. So it's completely random, essentially. Now, the good news though is that these bigger models over here, so the models with the big training sets are actually quite robust. And if you want to understand why these errors come about, you can look at an individual trajectory. So this is an MD trajectory for this molecule, and this is the energy error over time. And you can see, initially, for the first 800 picoseconds or something of this MD, there's really nothing that is happening, so the error is quite small and the model is reliable. But then it reaches a point where it does something very stupid. Now you have a hydrogen atom bridging these two carbon bonds, and you have basically these bond breaks for no reason. And this really shows you that detecting this lack of robustness requires you to really also probe your model in a kind of more extreme situation, or at least in the situation where you actually want to apply it, right? So it's all well and good to do test training splits and look at tested errors, but you really need to also look at how does my model work in the field. Now, that was the bad news, right? So robustness is not always a given, but the good news is if you have a robust model, it can extrapolate. So QM7X is called QM7X because the biggest molecule has 7 non-hydrogen atoms. So this means the biggest molecule here is basically a benzene with one, toluene group or something like this. And you can go see if we do a prediction on significantly larger molecules that have, for example, these fused rings that are not in the training set, they cannot be, or even here a small peptide. The GenNet model, and these are the red points here, still has a really robust prediction. Right? It might have some systematic errors, forces are also very well predicted. The Schneid model, trained on the same training set size, does not have that robustness. And so again, you see, you need big data to be robust and transferable in this way, but it also makes a difference what kind of model you're using. All right, and I'm almost out of time, but just as a complement to what we just heard also about the universal models, so there's now also a universal maze model, maze MP0, that has a very long author list, and the long author list is mainly due to the fact that this model has been really, so it's trained on the materials project and on relaxation geometries, but it's been tested in a lot of different situations. So it's been tested for catalysis applications, different surface questions, molecular questions, molecular hydrogen under pressure, dissolution of ionic systems in water, and all these things. So some people from my group have also been involved in this, and I have to say I was really, really surprised how well it extrapolates. So let me just give you 2 little examples here. One is not really a strong extrapolation, but this is just a test we did, where we essentially did a lot of atom substitution. So we took known compositions from the materials project, and we substituted the elements into all kinds of other compatible crystal structures and relaxed those with maze MP0. And you can see that a lot of these, so this is a plot of the energy deviation from the reference and the volume deviation from the reference. A lot of these actually end up here at 1, 0. So that means they have the same volume as the reference and the same energy as the reference. And this is a log scale histogram. So this means that if you kind of perturb the configuration and you do a local relaxation, many of them end up in the same structure. And what's also interesting, you have quite some density here below 0. So this is below the convex hull of the materials project. So the model is predicting a lot of new materials as well. And if we now validate this with DFT, you actually see that we have a bunch of discoveries here of new structures that are below the convex hull in materials project for materials that are already in materials project. So I think this is quite interesting. And in fact, we did the same thing with N3GNet, and there's also a lot of discoveries there. Yeah, different ones, but it's quite interesting. So I'd be happy to get some opinions on this as well. And then the last thing, so this is really an extrapolation. So this is water benzene, randomly initiated box, and just molecular dynamics on this. And you can see that we basically observe phase separation between water and benzene. And this was really unexpected for me because the materials project doesn't contain any liquids, it doesn't contain any of these kind of biphasic systems, but nonetheless, this is robustly predicted. And we also did other things, we did water ethanol, for example, and that doesn't mix. So it really has surprisingly robust extrapolative capabilities. Nonetheless, of course, you shouldn't use this blindly, you should always validate and test it. And I think really the big trend here is to use these kinds of models and refine them, retrain them on a specific application, because that kind of then brings together the big data limit, right? So the work here on the big data has already been done in a way for you, and now you can use your small data for a specific application, refine the model, and have a pretty robust and reliable model. All right, so that's all I wanted to present. So just to summarize, I think there's kind of important concepts that have really taken off now in the field that are kind of standard. So for the small data regime, this certainly is active learning, and using physical insights and inductive biases to make your models robust, right? If you have little data, then you shouldn't waste the model's time to learn stuff that you already know. Right? So the model should only learn the stuff that you don't know. And then when you are in this big data regime, really these modern graph neural networks have really transformed the field in my view. And you can now have these universal models. And in my case, that would be the GenNet model, which we trained for organic molecules. I can recommend it. And the LACE P0, where it's also been involved, and we are now using a lot for basically inorganic and solid systems. Yeah. And finally, I want to thank the people who did the work here. So I already showed their pictures during the talk, but nonetheless, thank you very much for them. And Gawa Chani for collaborating on the maze stuff, Stefan Billemann for the GenNet, and Carsten Reuter for basically all of these different projects. And yeah, thank you for your attention.
Thank you for the excellent talk. Any question?
You showed a work that was able to find some crystals that were below the convex hull. I'm curious if you looked at the phase diagrams and to international crystal database and so on to see if there are compounds that are similar to this, but maybe known in a disordered state or something like that, because this is something that can happen when you do this kind of...
Yes, that's a good point. And so, no, we haven't looked at disorder compounds, and we haven't looked at the, well, we have looked at the ICZ and we have looked at the materials project. So we've compared it with everything that's in there. And so these numbers here are relative to the current materials project convex hull. But I think, yeah, certainly the disorder is a tricky topic there. So they might, the point is they might not be new, is what you're saying.
They might be ordered versions of something
that is already known, yeah, that's true.
It's quite similar, like
Yeah.
pseudo-SUS.
Yeah.
Thanks, very interesting. So speaking about force field for organic materials, now, I'm particularly in a soft material like polymer or like large macromolecule and so on. There, if we do the old-fashioned way, bond constant sort of important but not that much, bond distance sort of important but not that much, we all care about the barrier within conformation.
Yeah.
And so if we do use your magic, then we're going to have models which appear to be fantastic even if the barriers are wrong or maybe not, and therefore they will have correct energy but the dynamics will be incorrect.
Yeah.
Or maybe not. Maybe you can explain this to me because it's critical for us to have the barrier right.
Yeah. So I agree that this is a very important topic. So basically the QM7X database we use for training here, it has isomers and it has conformers and it has non-equilibrium structures that come from essentially doing normal mode analysis and then doing displacements along the normal mode. So basically vibrations around the minimum. It does not have explicitly the barriers between the conformers, and this is also not something that we check. I can recommend though there's a newer model which is called MACE-OFF, so it's MACE Organic Force Field, and that has been trained on a much bigger database that explicitly also includes barriers. It has also been benchmarked to rotational barriers and these kinds of things, and it's quite robust there. And they've even benchmarked it also for lattice energies and this kind of thing, where it's not great, right? Because it's only been trained on, I think, dimer structures and not on solids. And this is really the next frontier, I would say. But I think it is feasible within the next year to really have a organic force field that does conformations and crystals and gaseous molecules. Not chemical reactions. I think that's another story, but. Those three things would already be quite useful.
Thank you, a very good talk. I have a question regarding the KQEQ method.
Yeah.
So, does the resulting electronegativities that you get out of the KQEQ equilibration, how do you do some sanity checks on them? Do you have bounds on the electronegativity? And how transferable are the local environment-based electronegativities across chemical systems?
Yeah, so we don't have checks on them. And there can be unintuitive things. It depends a little bit. So, for example, if you train your model on energies only for sodium chloride, what can happen is that the chloride is positive and the sodium is negative, right? Because there's no constraint there. The Coulomb interaction is symmetrical, right? So the result is correct from the perspective of the machinery potential. The electronegativities themselves are a little bit ill-defined, so we don't put bounds on them because only the differences matter for all of the properties. What we typically do is that we're a bit conflicted about this. So basically, what helps is if you add some population analysis information, because that gives you you use Hirschfeld charges, for example, right? And that's in fact what JB does for the fourth generation networks. I don't like to rely on the Hirschfeld analysis though, because or any other population analysis, because again it's ill-defined and it doesn't give me the right electrostatics necessarily, right? So what we do is we use these kind of as a regularization. We put in population analysis with a small weight, sometimes also only during initial training steps, and then we remove them. And that puts us in the right ballpark. But we usually want the charges that come out to be optimal for energies, forces, dipole moments, and this kind of stuff, and not to just fit some population analysis.
That in certain systems, you actually have a much simpler way, which is I just assign hard charges to the different species. Like for example, sodium will be 1, chlorine to be -1.
Yeah.
And then I let the machine learning potential learn the difference between whatever electrostatic interaction versus the local environment component.
Yes.
And at least for certain systems, that actually already gets you, I would say, 90% of the way.
Yeah. That's a good point, yeah. The point where that doesn't work is if you have changes in oxidation state, right? If you have that hydrogen in water and then it goes to the surface or it deprotonates, that makes it a little bit harder. But I agree, it's in general a good idea. Yeah.
Any other question? So if not, let's thank the speaker again.
Thank you very much.